So, welcome everyone to the week 9 discussion of this course, Social Networks. And this course is originally taken by Professor Sudarshan Iyengar, Professor and Head of the Department of Computer Science and Engineering of IIT Ropar. Myself, Ayan Paul, I am a PMRF research scholar from IIT Kharagpur and I am a TA of this course. By TA, my duties are I will solve some of the question that will be very similar to your assignment, so that whenever you will be solving the assignment it will be easy for you. But before that, what I prefer is always discuss what has been discussed in this week, so that it will be easy for us whenever we are tackling the question, okay, rather than directly go to the question, okay. So with that, let's start the discussion. So today we will be talking something about power law, okay. So power law describes a relationship where a small number of nodes have extremely high connectivity and a large number of nodes have very low connectivity. Okay, so two things are important. A small number of nodes have extremely high connectivity, whereas large number of nodes have very low connectivity. So that is known as power law. Okay, Now, mathematically, how we describe it? Mathematically, we describe it by this: P, probability of that a node has degree k. We write it as p k. Okay, that is approximately equal to k to the power minus gamma. Okay, gamma. What is gamma? Gamma is some constant. Okay, typically its value is between 2 and 3 in case of a social networks. So, what does this mean in social networks? What does this power law means? So in platforms like Instagram, X or YouTube, a few influencers have millions of followers. Most users have very less followers. This creates a highly unequal distribution of connections. Okay. This this is the graph of power law. This is the graph of power law. You can see this y-axis is percentage of nodes, and this x-axis is the degree. Okay, so when the degree is less, you will have many number of followers, but as the degree is increasing, you have a very less number of followers to that particular degree. Okay, so that is the power law. Now key characteristics, heavy tail distribution. Heavy tailed means you can see the curve is tailing in. Okay, so this is a heavy tail distribution. So unlike normal distribution, what is normal distribution we will see in the next slide. Unlike normal distribution, extreme values are common. No typical or average node represent the system. Okay. Next, there can be a presence of hub. Highly connected nodes that will be called as hubs. Okay. Example: celebrity account, viral creator. And third is there is a scale-free property. Okay. So the network looks similar at different scales. Whether you zoom in or zoom out, you still see very highly connected nodes, many sparsely connected nodes. Okay, so that are the three characteristics of the power law distribution. First, it is heavily tailed, as you can see from this curve also. It is heavily tailed. Second, there should be presence of hubs. What is hubs? Hubs are users or nodes with high number of degree or high connection. Okay, so that are hubs. And third, there will be a scale-free property. The nodes look similar at different scale. Whether you zoom in or zoom out, you still see very highly connected nodes and many sparsely connected nodes. Okay, so these are the three characteristics, or the three key characteristics of the power law distribution. Okay, so this is what we have studied in the first slide about power law in social networks. What does that mean? A small number of nodes have extremely high connectivity and a large number of nodes have very low connectivity. Okay, so this is what power law suggests. Okay, now let's move on to the next things, that is, why do normal distribution even appear? Okay, so that is another question. So last slide we are talking about power law, but most of the real life things that we encounter, that follows a normal distribution. Okay, so why does normal distribution appear? A normal or Gaussian distribution, you might have heard this thing as Gaussian curve. Okay, Gaussian curve or Gaussian distribution. So a normal or Gaussian distribution emerges when many independent small random factors combines. Each factor contributes a little without reinforcing others. This is explained by a theorem known as central limit theorem, or CLT. Okay, so central limit theorem. So you can see there are many example of this Gaussian distribution. Gaussian distribution, what kind of curve? We have a bell-shaped curve. For example, height of people, make a note of adult heights of people in the town. You can see that will follow a power law. That will follow a Gaussian distribution. Okay, so Gaussian distribution, you can see height. There will be a mean at which you can see the Gaussian distribution peaks, and around it there will be a equal type of distribution. Means below the mean or above the mean, you can see a equal type of distribution in case of this Gaussian distribution. X-axis is height and y-axis is percentage of people here. Okay, so that is the first example. Second example can be IQ of people. So IQ of people, again you can see it follows a bell curve. Okay, so this is known as a normal distribution. Okay, normal distribution. So again you can do is sum of two random variables. Okay, so you just took the sum of two random variables, and again it will you can see it will follow a Gaussian distribution. Why? Because many independent small random factors combine and they give you a distribution. So that is why it is that is why you can see a central limit theorem or Gaussian distribution here. So examples: human height influenced by many genes plus environment. So that is why it follows Gaussian distribution. Measurement errors, exam scores. Okay. So key property has a clear mean and variance. What I was telling, mean and variance. Okay. So what is mean? The central. If you see the central of the Gaussian curve, okay, that will give you the mean. Okay, mean of the distribution. And variance. What is variance? Variance is square of standard deviation. So this middle thing, that is known as mean. Okay, so let me write it as mu. Okay, mu or mean. And this and this, so this end will be known as mu plus sigma. What is mu plus sigma? Sigma is nothing but standard deviation. And what is standard deviation? Standard deviation is root over this variance. And what is this? That is the left extreme. So left extreme is mu minus sigma. So mu plus sigma at the right is extreme, and mu minus sigma, this is mu minus sigma. Okay, mu minus sigma at the left extreme. So I was talking about this. So this portion you have mu minus sigma, middle you have mu, that is the mean, and mu plus sigma, or mu is the mean and sigma is the standard deviation. So mu plus sigma at the rightest extreme. Okay, so that is so this is the key property of Gaussian distribution, has a clear mean and variance. No extreme inequality. We are not seeing any inequality here. Means it is properly skewed. Okay, it is not right skewed or not left skewed. It is properly skewed. That means if you keep a mirror here, you can see the similar reflection on the mirror that will complete the curve. Okay, so that is no skew. No extreme inequalities, no dominant outliers. Okay, so there are no outliers that dominates. Okay, so that is why no dominant outliers. So these are the three key properties of your Gaussian distribution. Why it looks like a bell shape, that is a Gaussian. So most values cluster around the average. Okay, most of the value that you will get, that definitely cluster around the average. Extreme values are rare. Okay, extreme values are rare. Symmetry, that I was talking about, deviations above and below the mean are equally likely. So this is about the normal distribution. And now, why power law emerges in WWW graph or worldwide web graph? Okay, so key idea here, growth plus preferential attachment. Okay, preferential attachment, that means new nodes that are added that have some preference. Okay, which to connect, whom to connect. Okay, the World Wide Web WWW is not random. Here Gaussian distribution, we are talking about small random factors. But whenever we are talking about why power law emerges in WWW graph, because here the WWW or World Wide Web is not random. It evolves through continuous growth, that means new pages are added, and bias linking, that means new pages linked to popular pages. Okay, so this is the thing. So you can see here, so that is why WWW it follows a power law distribution, not a normal or Gaussian distribution, but rather a power law distribution. Okay, because we have this continuous growth and bias link, new pages added to popular link. So mechanism, why you are getting this curve? A web page with many links is more likely to receive new links, that is rich gets richer. Okay, so that is the thing. So a popular blog is more likely to be cited than a new unknown blog. So definitely whenever people will follow it, they will follow the already more popular links. Okay, so that is why you are getting this type of curve. Okay, that means a small number of pages have very small number of nodes have very high degree and other nodes have low degree. Okay, so this is the thing. So result, power law distribution, few pages get millions of links, most pages get very few links. Okay, so this is why www or World Wide Web or any social media network webs, they follow a power law graph rather than normal distribution graph. Okay, but most of the random things in nature, they follow the normal distribution graph or the bell shaped curve. So there I have kept a table, okay, for a comparison between the normal distribution and the power law. And first feature is process. Okay, so normal distribution, whenever we are talking normal distribution, so it is additive and independent effect. Okay, but here it has power law, it has multiplicative or feedback driven. Okay, growth, it is static or random in case of this normal distribution. Here it is dynamic and evolving in case of this power law graph. Okay, bias, it does not have any bias in case of normal distribution. Okay, but here www graph or power law graph, it has a bias. Okay, so strong has a strong bias towards the popular nodes. Outcome equally around the mean, here extremely inequality. Okay, and then example is height noise, and here power law example is www links or followers. Okay, so this is the difference why in nature you see more normal distribution curve. Okay, but in social networks you see power law curves. Okay, this is the only difference. Okay, because one line answer rather, if I say, because in nature most of the cases they follow a random distribution. Okay, random means there is no bias and things are randomly added. But here it is not random, it has some bias. Okay, what type of bias? The new pages or new links that will add, they will always try to prefer linking to already the strong ones. Okay, in case of strong ones or popular ones in case of your social media networks. Okay, so this is the thing about why social network follows power law and nature rather follows the normal distribution. Okay, so this is the thing. Now visualization of the of this power law. Okay, visualization of this power law. So if you plot x-axis number of connection degree and y-axis is the number of nodes. Okay, so x-axis is the number of connection or degree and y-axis is the number of nodes. Okay, so then on a normal log scale it is highly skewed. Okay, normal log scale your power law looks something like this. Okay, that means it is skewed. Okay, but if you plot this same curve in a log scale, what you will see? You will see a straight line. Okay, so this straight line is the signature of power law. Why this is happening? Because whenever we are talking about power law, like it is a function of fk 1 by k square, or what I told you, it is like p k will be equal to k to the power minus gamma. Okay, so this is the equation of power law. But whenever we will log both the sides, so what will happen is, if I will log this, so what will happen? Log of fk, that will be equal to minus 2 log k. Okay, so what will happen is, this we can log of fk, we can tell it as y, and this minus 2 log k, that we can call it as mx. Okay, y equals to minus mx. Okay, so y equals to minus mx, what will be the curve? The curve will nothing but a straight line. And as there's a minus, because power law is the coefficient is minus. Okay, 1 by k square, that means k to the power minus 2. Okay, that means k to the power minus 2 or minus 3 rather. So that means what you can infer is the slope of the straight line curve, that will be nothing but your receding slope. Okay, not a accelerating slope but a receding slope, because minus is there. Okay, minus 2 or minus 3 is the slope. So that is why your curve is already is straight line, but the slope is receding. Okay, so this is how you can visualize the power law. Okay, now we have a very important phenomena known as rich get richer phenomena. So what is this rich get richer phenomena? The rich get richer phenomena is a fundamental concept in network science that explain why a few individual or nodes in a social network accumulate a disproportionately large number of connections while most others have very few. The process is also known as preferential attachment or cumulative advantage. Okay, again I am repeating, the rich get richer phenomena, this is actually a characteristics of power law. Okay, is a fundamental concept in network science that explain why a few individual or nodes in a social network accumulate a disproportionately large number of connection while most others have very few. This process is known as preferential attachment. Okay, this word you must always remember, preferential attachment or cumulative advantage. Okay, in social network, nodes that already have many connections are more likely to receive new connections. Mathematically, the probability that a node receives a new connection is proportional to its current degree. Okay, so mathematically, if I tell you, so node receiving a new connection is proportional to its current degree. Okay, so current degree is, let's say current degree is ki by sigma kj, sigma j kj. That means in the denominator all your other nodes will all the degree of other nodes will come, and in the above the degree of its own the degree of the own node will come. Okay, so ki is equal to number of connections of node I, thus nodes with higher ki gains link faster. Okay, so what is the mechanism behind this phenomena? The process typically works in two steps. First is network growth. Okay, social networks constantly adds new nodes, new users, website or influencers. And second step is the preferential attachment. So new nodes prefer to connect to already popular nodes because they are more visible. Okay, they appear more trustworthy or influential, and algorithm recommends them more frequent. Okay, so that is the reason why you are seeing this rich get richer phenomena. Okay, so two mechanism. First is network growth. Social network will constantly add the new nodes, and the new nodes added. Second is they will always try to for preferential attachment. Okay, they will prefer the already popular nodes. Why? Because they are more visible, they appear more trustworthy or influential, or the algorithm that will always recommend them more frequently. Okay, so this phenomena is collectively known as rich get richer phenomena, and this is one of the most important outcome of the outcome or characteristics. Outcome would be a good word. Outcome of the power law. Okay, so this is the thing about rich get richer phenomena. Now we have this rich get richer phenomena in the model known as Barabasi-Albert model, or commonly known as BA model. Barabasi-Albert. Okay, Barabasi-Albert, or commonly known as BA model. So what is the core idea? Core idea is nothing but your preferential attachment. In BA model, the rich get richer phenomena is built into the model. How it works? The network grows over time. New nodes are added. That is network growth. Each node connects existing node with a probability proportional to their degree. Okay, so new node pi directly proportional to ki, what we have just seen. Okay, pi is directly proportional to your ki. Okay, so node with high degree ki get more links. Result, early nodes gain advantage, first mover advantage. Okay, that this advantage is known as first mover advantage. A few nodes become hubs. Okay, degree distribution, it follows a power law. So interpretation, the BA model explicitly models the rich get richer phenomena where popularity reinforces itself. Okay, and second thing, we have something known as Erdos Renyi Model. Okay, this is random model, and here the power law or the no rich get richer effect is followed. Okay, how it works? Nodes are connected randomly. Okay, not sequentially or over time, but nodes are connected randomly. Each pair of nodes has equal probability of being connected. That is, it will connect with some HP. Okay, so most nodes have similar number of connection. Degree distribution is binomial or Poisson. No hubs emerge naturally. So interpretation, in ER networks, popularity does not influence future connection. So rich get richer does not occur. Okay, so what we have learned? We have learned about two models. One is your BA model. in which richer phenomena is built into the model, and then we have ER model, Erdos Renyi Model, in which no rich get richer phenomena is followed. Okay, in this the network grows over time. In BA model, network grows over time, and each new nodes connect to the existing nodes with probability proportional to their degree. That is, Pi is proportional to Ki. Nodes with higher degree Ki gets more links. Okay, but here in ER model, nodes are connected randomly, and each pair of nodes has equal probability of being connected. It will connect with the probability P. Okay. So result in the BA model, early nodes gain advantage, that is first mover advantage. A few nodes become half degree distribution. It follows a power law. In this ER model, most nodes have a similar number of connection. Degree distribution is binomial or Poisson. Okay, no halves emerge naturally. Okay. The BA model explicitly models the rich get richer phenomena where popularity reinforces itself. In ER model, popularity does not influence the future connection, so rich get richer does not occur. Rich get richer phenomena, it does not occur. Okay, so this is regarding the rich get richer in BA model and ER model. Let's see the institution. BA network, few critical hubs hold everything together. ER network, all nodes are roughly equally important. Okay. This is the you can say a differential table that I have given you. BA model and Erdos model. Attachment here, it is preferential in BA model, it is random in ER model. Rich get richer, it is present in the BA model, it is absent in the Erdos ER model. Degree distribution, it follows power law in BA model, it follows binomial or Poisson distribution in ER model. Hubs, it is created in BA model but it is not created in ER model. Okay, so this is about the difference between the BA model and the ER model. Now we have this last theory topic, that is force versus random removal of nodes. Okay, so random removal failures, what happens? Nodes are removed randomly. In scale free BA networks, most nodes are low degree. Hubs are unlikely to be removed. Network remains largely intact. Okay, so this we are understanding. If random removal or failure is occurring, then how this models will behave. Okay, so if random removal or failure will occurring in BA model, what will happen is most nodes are low degree. Okay, hubs are unlikely to be removed, so networks, it will remain largely intact. But in ER model, nodes are similar, random removal affects structure more uniformly, so there is gradual degradation in case of ER model. Now, when we have this force removal or targeted attacks, here it is a random, okay, but if we have a force removal, so what happens? High degree nodes, hubs are deliberately removed. So in scale free BA model, removing hubs destroy the connectivity, so network quickly fragments here. And in ER networks, no strong hubs, removal has more uniform effect, so less dramatic collapse will happen. So removal type, random removal, highly robust in case of BA and moderately affected in case of ER. But in targeted removal, it is highly vulnerable in case of BA and less sensitive in case of ER. Okay, so this is the summary when we will randomly attack or randomly remove the nodes. Okay, in case of BA model and the ER model. So topics on which week 9 assignment are based. Okay, so let me just revise what we have learned. So what we have learned so far. So today we have learned something known as power law. Okay, power law. What is power law? Power law follows the equation P K equal to or approximately equal to K to the power minus lambda. Okay, so lambda is a constant, usually 2 or 3 in social network. Okay, so what is power law? Small number of nodes have extremely high connectivity and large number of nodes have very low connectivity. Okay, so this is the power law. Okay, what is the graph of power law? This is the graph of power law. You can see here that When the degree is less, you have more percentage of node, but when the degree is high, you have less percentage of nodes. Okay, so this is the power law. Okay, now World Wide Web, they follow the power law, but your most natural cases like height, okay, height in a city or IQ of people in a city, they follow a distribution known as normal distribution or Gaussian distribution. Okay, why? Because here the central limit theorem is followed, and what is happening is many independent small factors combine, and this is explained by central limit theorem. So here we have a clear mean and variance, no extreme inequality is happening, and no dominant outlier is there. Okay, so the curve that we are getting, it is a bell shaped curve. Extreme values here are rare, and there is a symmetry. Okay, deviation above and below the mean are equally likely. Okay, so this is normal distribution. But in power law emerges, when power law is emerges, like in this www graph or World Wide Web graph. So here what you can see that there is a preferential attachment. Okay, so it is not random, unlike this normal distribution. It is not random, it evolves through continuous growth and biased linking. Okay, here the linking here is biased, so new page added to popular pages. Okay, so it follows the preferential attachment. New page, whenever it is added, it follows a preferential attachment, not random but preferential attachment. A web page with many links more likely to receive new links, so rich get richer. So this is the thing. So few pages will get million of links. Most pages get very low links. Okay, this is what we have read. We have seen how we can visualize the power law. Okay, so this is the curve of the power law, where we can write it as function of k will be equal to 1 by k square or k cube, whatever. Okay, 2 to 3. The power is between 2 to 3 usually. So this curve is not linear, but when if we log on both sides, that is log fk, what will happen is it will be minus 2 log of k. Okay, so that will be following y equals to minus mx. So that is why the curve that we will get from log k on x-axis and log fk on y-axis, the curve will be a straight line curve. Okay, straight line curve with a receding slope. Okay, why receding slope? Because it is minus mx, minus m, the slope is negative. Okay, so that is why you will get a receding curve. And then the result of power law is this rich get richer phenomena. Okay, rich get richer phenomena. Few individual or nodes in a social network accumulate disproportionate large number of connection, while most others have very few connections. Okay, so this is the rich get richer phenomena. It happens in two steps. First is network growth. Social network adds new nodes or new users, and then we have this preferential attachment. New nodes prefer to connect to already popular nodes. Okay, so these are the two things. That is why we get the rich get richer phenomena. And here the new nodes that are added. Okay, the nodes with higher degree gain links faster. Okay, so that is why we have this equation. So pi is directly proportional to ki. What is ki? Ki is the number of connection to node I. That means more is the number of connection to node I, more it will get the probability of connections. Okay, so this is the rich get richer phenomena. And then we have this two model. One is BA model and one is ER model. BA model, it follows the BA model, it follows the rich get richer phenomena. ER model, it does not follow the rich get richer phenomena. It is a random event. Okay, the connection here is a random event. The connection here, it follows the preferential attachment. So that is why BA model, it models the rich get richer phenomena, where ER model does not. Okay, the curve in which we get in the BA model, that will be power law curve. But the curve here that we got it, we get a binomial or Poisson distribution curve. Okay, so that is about ER model and BA model. Now if we remove the nodes, okay, so that is known as attack survivability. Okay, so there are two types of attack. One is random removal of nodes. In case of random removal of nodes in BA networks, what will happen is network remains largely intact, because hubs would not be be largely intact, and what will happen is most nodes that are removed, that will be low degree. So that is why That is why here you will have you will have a high robustness in case of your BA network to random removal, but in ER network you will have a moderately affected removal. Okay. Yeah, so in case of random removal, you in your BA network, as BA network is highly robust. Okay, so that is why it will remain largely intact, because what happens when you are randomly removing the nodes, what will happen is, most nodes in the BA network, those are low degree nodes. Okay, so hubs are unlikely to be removed, so that is why it will have less effect when you are randomly removing nodes in the BA network. But in ER network, when you are randomly removing the nodes, random removal affects the structure more uniformly, so you will have gradual degradation. Okay, so that is more, it will be moderately affected in case of random removal. But in case of forced removal, if we are targeting the high degree nodes, what will happen is, this BA network, the network quickly fragments. Okay, so it is, as it is highly vulnerable. And then in ER networks, no strong hubs are there, so removal has uniformly effect. So again, it is less sensitive to the random removal. Okay, so this is the difference between removal of nodes in case of BA network and ER network. In two cases, one is random removal and second case is targeted removal. Okay, so this is regarding theory that we have discussed in this week. Now we will be talking about topics on which week 9 assignment questions are based: introduction to power law, why do normal distribution appears, power law emerges in WWW graph, rich get richer phenomena, rich getting richer phenomena, BA model, ER model, and then we have this force versus random removal of nodes, attack survivability. Okay, so this is the first case. What is the first case? The curious rise of Chef Rima's recipes. Chef Rima, that is the name of the chef, she started a food blog in 2015. For 2 years, she had a modest audience, but one day her spicy ramen hack went viral. People began linking to her old recipes too. Over time, her blog started appearing at the top of the Google for anything food related. New food bloggers started linking to her recipes, often ignoring other equally good blogs. This is not just fame, it's preferential attachment at play. Okay, so this is the case. So now theories that we are required for our case one, the curious Rima's recipes case. Network science and complex network. So what is nodes here? Nodes is the blogs or website. What is the edges here? Edges are the backlinks or hyperlinks. Okay, here we are getting preferential attachment. This is the central theory of this case study. New nodes prefer to connect to the already well connected nodes. Early success leads to disproportionate long term advantage. This explains why Rima's blog dominate the search results. Scale-free network, few highly connected nodes, many low degree nodes, a heavy tailed or power law degree distribution. And power law degree distribution, how it appears as a normal curve or a log plot, we all know. First mover advantage, so student must distinguish content quality is not equal to visibility. Okay, early entry plus accumulated links matter more than the merit alone. Okay, and then network growth, preferential, non-random attachment, and random attachment. Random attachment is given by ER model, popularity based attachment or preferential attachment is given by the BA model. And then role of hubs and networks. Hubs are critical for connectivity. Removing a hub can fragment the network. Scale free network are fragile to hub failure. So this case study primarily tests concept from network science, spatially preferential attachment, scale free networks, power law degree distribution, random versus preferential growth models, and the structural importance of hubs. Okay, so let's go to the question answer part. I don't see anyone in the class, so okay, I will discuss it and you can see the video in the YouTube. Okay, so what kind of network structure is most likely forming as Rima's block gains more backlinks? A symmetry tree where each node has similar number of links. A centralized star where one node control all connections. A network with a few blocks having lots of links, most with a very few. A chain where each block links only to next in time. Okay, so what will be the correct answer? The correct answer will be C. Okay, uh, a network with a few block having lot of links and most with very few, like Rima's one that will have lot of links, and other ones that there will be a very few links. Okay, so Rima's block is gaining a disproportionate number of links compared to other block. This is preferential attachment where the rich get richer phenomena is observed. Most blocks have few links, have few, like Rima's have many. A network with answer will be a network with a few blocks having lot of links and most with a very few number of links. So option C is the correct answer over here. Okay, so option C is the correct answer for question number 1. Okay, let's move to the next question. If we plotted the number of backlinks per block on a log graph model, what pattern would you suggest? Would suggest a power law. Perfect S-shaped curve, a straight line diagonal line, a steep curve that flattens a circular loop. Okay, so what will be the answer? It is a power law curve, but it is on a log graph, log scale. So as power law curve in a log scale is nothing but a diagonal straight line. Okay, diagonal straight line with a receding slope. Okay, not with a accelerating slope but a receding slope. That means the slope is negative. Okay, so here it will be like here it is log of fk. Okay, log of fk of log of pk. Let's say log of fk here, log of fk. Okay, here it is log of fk, and in x-axis it is 1 by k square, right? Means log of k. Okay, log of k. So log of fk and log of k, will be nothing but your straight diagonal line with the receding slope, because it is following a power law. And what is the equation of power law? Power law equation can be like fk equals to like something k to the power minus gamma. Okay, k to the power minus gamma. Okay, and gamma here is like 2 or 3. Okay, whatever. Okay, gamma 2 to 3, whatever. Okay, so this is, and when we will see log of this, like log of this and log of this, what will happen is like log of fk, log of fk log of fk will be equal to minus of gamma log k. Okay, minus gamma log of k. Okay, so this is nothing but this is y equals to minus gamma. Let's say this is m, gamma equals to m, and this log k is x. Okay, so y equals to minus mx. So that is why this curve is a straight line curve with receding slope. Okay, so this is the answer. Power law distribution appears linear on a log plot. This is typically in networks with hubs. So it is a answer will be a straight diagonal line. Option B is the correct answer over here. Okay, now let's move on to the next question. A new blogger, Nina, creates amazing content, but barely anyone links to her. What concept best explain why she is struggling? Homophily, first mover advantage, rich get richer dynamics. Sorry. The rich get richer dynamics, or option D, degree normalization. So definitely she is suffering from this rich get richer dynamics, because blogger like Rima, they are already rich, so they are getting more followers, but Nina, as she is not rich in terms of followers, okay, as she is not that rich, so she is not getting any followers, okay. So that is why even though Nina has quite content, she is new and has a few links, has quality content. Even though Nina has quality content, she is new and has few links. Rich get richer dynamic preferential attachment explain why early popular nodes attract the most links. So option C is the correct answer. Okay, very easy. All this are related to your power law. All this question, all the three question that we have discussed, it is related to your power law. Okay, so this is the thing. Now let's move on to the next question. Suppose 10 new food bloggers join every week. If each connects randomly to any existing blog regardless of the popularity, which model best describe this growth? BA model or ER model or Strogatz model or structural balance model. So we have learned about two model, BA model and ER model. BA model is preferential attachment, okay. PA, preferential attachment, but this ER model is your random attachment, RA, okay, random attachment. In this question what has been asked, if each connects randomly, okay, each connects randomly to any existing blog regardless of popularity, that means they will follow the ER model, okay. So option B is the correct answer. So random attachment without considering a node popularity is the characteristics of your ER model, network model, not preferential attachment. So option B is your correct answer. Okay. Let's move on to the next question. Rima's blog suddenly disappears from the web. Many recipe chains that dependent on it are now broken. What does this say about the role of the hub nodes? So they can be removed with no consequence. They only matter during network creation. Their failure can fragment a network. Their removal leads to a better decentralization. So Rima's block suddenly disappears. So what will happen is, this is attack of hub. So when the hub is attacked, and this is what model is this? This is a BA model. That is BA model. Okay, not ER model. So that is why when this type of things happen, that is hub is removed. So that means the attack is not random, but attack is targeted. When you have a targeted attack, then their failure can fragment a network. So option C is the correct answer. So hub connected many parts of the network, removing them fragment the network. So their failure can fragment a network. Option C is the correct answer over here. So by this we have end our case number 1. Okay. So by this we have end our case number 1. We will move to the next case, that is case number 2. So let's start the case number 2. Case number 2 is the title is the fortune of the friend book. Friendbook is a new social media app. Every user can follow others and post content. The early users who joined Friendbook quickly gain followers and become influencers. New users tend to follow the already popular ones. Okay. Now, what theory that you are required for case number 2? Social network basic, that is node will be users here. Edges will be follower relationship. There will be directed links. Okay. That means if A follows B, that does not imply that B follows A. Okay. And preferential attachment will be there. New users prefer to follow already popular users. Okay. Anything? Okay. Yeah. New users prefer to follow already popular users. Early popularity compounds over time. Explain why influencer emerge naturally. Okay. Power law distribution. Most users have very few followers. Few users have extremely many followers. This inequality is not random. Scale-free networks, preferential attachment leads to scale-free networks. Influencer act as hub. Degree distribution follows a power law. Network growth models. BA models, growth plus preferential attachment. ER model, random connection. No popularity bias. Random versus non-random attachment. Random attachment relatively equal degree. Preferential attachment inequality and hubs. Long-term network effects and path dependence. Early advantage persists even without new activity. This is called initial degree inertia or preferential lock-in. Networks have memory. This case study assesses understanding of social network growth, preferential attachment, scale-free networks, power law degree distribution, random versus preferential models, and long-term persistence of node centrality. Okay, so this is regarding case number 2. So, what mechanism is best? Describe how influencers on friend book gain most of their following. Option A, reciprocity, richgetricher, structure equivalence, or clustering coefficient. Okay. So these are the 4 options. What mechanism best describes how influencers on friends book gain most of their following? Reciprocity or the richgetricher. Option C, structural equivalence or clustering coefficient. So option B is the correct answer, that is richgetricher. So early user who gain followers first continue to attract more followers. This is classical preferential attachment, also called as the richgetricher phenomena. Richgetricher phenomena. So option B is the correct answer over here. Okay, very simple question. Now let's move on to the next question. Question number 7. You analyze the distribution of followers across users and find a few who have over 10k followers. Okay, 10,000 followers. Okay, while most of them have under 50. Which phenomena is likely to play? Uniform distribution, Gaussian distribution, power law distribution, or binomial distribution? So power law distribution is followed in case of this friend book network. Okay, because it is a social media network, and you can see most have very low degree, most have very low friends or followers, and very less have very more followers, like very few have more than 10,000 followers, and most have under 50 followers. So it follows the power law distribution. Option C is the correct answer. So this describes a heavily tailed distribution where a few nodes have a very high degree and most have very low degree. So that is power law distribution. Option C is the correct answer over here. Okay. Question number 8. If we model the growth of friend book using BA model, what feature must present in this network? Equal probability of linking to any user, preferential attachment to high degree nodes, random triadic closure, or D, negative tie. So BA network, BA model or BA network, that means here preferential attachment to higher degree nodes is there. Okay, and if you have random, if you have this ER model, okay, random attachment is there, then there will be equal probability linking to any user. But it is BA model, so option B is the correct answer. If it is a ER model, then equal probability of linking to any user, so option A will be correct. Okay, but as it is a BA model, option B is the correct answer. Okay, so BA model, BA network group preferential attachment, where new nodes are more likely to link to higher degree nodes. Preferential attachment to high degree nodes, option B is the correct answer. Okay, so again a very simple question, but all these questions are important. Simple, but all these questions are important. They will give you a insight about the topic, which is very important. Okay, now let's move on to the next question. Question number 9. You create a model where new user connect to randomly to 3 existing users. Which model are you likely implementing? Okay, new user connect randomly to 3 existing user. Okay, this random word is important. As random word is important, so option B is the correct answer, that is ER model. Okay, BA model is preferential attachment, ER model is random connection. So option B is the correct answer. Okay, so random connection without considering popularity corresponds to ER model. So option B, that is Erdos Renyi Model, is the correct answer. Okay, option B is the correct answer. Let's move on to the next question. You observe that some influencer retain their popularity even after months of inactivity. What long-term network effects could be responsible? So again I am repeating, you observe that some influencer retain their popularity even after long month of inactivity. What long-term network effect could be responsible? rewiring probability, memory decay, preferential lock-in, or option D, initial degree inertia. So option C is the correct answer. That is okay. Option C or D, whatever. It is also known as preferential lock-in, but initial degree inertia. This is also called as initial degree inertia. So according to me, C as well as D is the correct answer. Both is true. But here C is given, D is given, so let's stick with the popular users keep attracting attention due to their already high degree, even without new activity. This is called as initial degree inertia. Okay, initially they have high degree, so that is why they are attracting. So option D is the correct answer, where early advantage persists over time. So option D is the correct answer. Okay, so by this we have end our case number 2 or the case second. Okay, so we have seen two cases. First case is your Rima's recipe. Okay, where due to her one recipe she got many number of followers. Okay, and second is friend book network. Okay, again this is a social network, social network, and both the cases the power law is followed. As power law is followed, then you have this preferential attachment and all these things. Okay, so the questions are 1 to 10 question is regarding this only. Okay, so let's see what our next case is. So we have case number 3, that is city grid shutdown. Imagine a smart city connected by a digital grid. Each traffic light, hospital, police station and internet hub is a node. A cyber attack starts removing nodes at random. Okay, so here what are the theories that are required for this city grid shutdown? So network robustness and resilience. Okay, random failures and targeted attacks. Okay, that we have already studied. Scale-free network, highly heterogeneous degree distribution, few hub nodes with very high degree, many nodes with very low degree. Degree distribution follows a power law. And then you have random failure versus targeted attacks, that also we have discussed. And fourth is role of hubs. Okay, hubs act as backbone of connectivity. Removing hub dramatically increases fragmentation. Hub reduces average path length and hold components together. Degree based attack strategy, removing nodes by degree ranking, that is targeted attack. Okay, is most damaging strategy. Random removal is less effective in scale free network. Network fragmentation and connectivity. What it means for a network to fragment, how the giant connected component collapses, why infrastructure network fail catastrophically when hubs are lost. This case study assesses understanding of scale-free network, hub-based connectivity, robustness to random failures, vulnerability to targeted attacks, and the role of degree centrality in network collapse. Okay, so this is the total theory that we required for solving this the question in this case. Okay, so let's see the questions one by one, that will clear your concept better. So under random removal, what type of network is likely to stay connected the longest? Option A, scale free network. Option B, a regular lattice. Option C, a complete graph. Option D, a tree structure. Okay, under random removal, what type of network is likely to stay connected the longest? Random removal. So when you have random removal, then option A, that is the scale free network, which follows the power law distribution, that will be stay connected the longest. Okay, scale free network have a few hubs with many connection and many low degree nodes. Random removal mostly hits the low degree nodes, leaving hubs intact. Therefore, a scale free network are highly resilient to random failures. So option A is the correct answer over here. Okay, let's move to the next question. Now the attackers target the highest degree nodes first. What is most likely outcome in a power law network? The network stay robust, only peripheral nodes are removed, the network quickly fragments, the average path length decreases. Option C should be the correct answer. Okay, the network quickly fragments, because we are talking about here, we are talking about the power law, which follow the power law. That means we are talking about BA network. Okay, BA network. We are talking about BA network, which follows the power law, and in BA network preferential attachment is very much important. So hubs emerge. Okay, so if you will remove the hub, so network will quickly fragment. So option C is the correct answer. Targeting hub removes the node that hold the network together. This causes the network to fragment quickly. So option C is the correct answer over here. Okay. So let's move to the next question. Why are scale-free network resilient to random failures? Okay. So most nodes are weakly connected. Most nodes have high degree. Hubs rarely get removed. They have equal clustering. So scale-free network resilient to random failure. Most nodes are weakly connected. Most nodes have high degree. Hubs rarely get removed. So option C is the correct answer. What happens is whenever we are talking about random failures, then the chances of hubs removal is very less because hubs are very less. Okay, so the chances to remove hubs is very low. Okay, so that is why option C is the correct answer. Scale free network, most nodes have a low degree and only a few nodes are hubs with a very high degree. When nodes are removed at random, the probability of hitting a hub is very low because hubs are rare. Since the hub remains, the network largely stays connected. So option C is the correct answer over here. Okay. Now let's move to question number 14. Which removal strategy would cause the most damage to a scale-free network? Random removal of leaf nodes, random node removal, high degree node targeting. Option D, removal based on age. So option C is the correct, high degree node targeting, that is targeting the hubs. Okay, so option C is the correct answer. Removing high degree nodes, hubs immediately fragments the network. Random removal is much less effective because it is mostly hits the low degree nodes. So option C is again the correct answer. Let's move on to the next question. Question number 15. Traffic collapses when a few central hubs fail. What does the scenario emphasize about scale-free network? They are better than random network in all cases. Their vulnerability lies in the hubs. All nodes carry equal weight. Centrality does not affect the robustness. So option B is the correct answer. The vulnerability of this type of network or the BA network that sorry, very sorry. Their vulnerability that lies on the hubs. So option B is the correct answer. The vulnerability came from the central hub, which are critical for network connectivity. So option B is the correct answer over here. So by this we have ended the third case. The third case is about attack survivability or the removal of nodes, either targeted ones or the random ones. Okay. So this is regarding the case number 3. We are left with other two cases. Okay, just 1 minute. Yeah. Yeah. So we are left with other two cases. Okay, just 1 minute. Yes, so we are left with other two cases. So let's start the case number 4. Yeah, option B was the correct answer over here. So let's start the case number 4. Startup stars and preferential attachment. A venture capital firm simulates startups ecosystem. Every new founder they meet tends to connect with already famous startup mentors. Founder who joined early have a better chance of getting funded. Theories that are required here, notes here are founders and members, edges here, professional connections, funding ties or mentorship links. Network evolve over time, not all at once. Preferential attachment is the dominant theory. New nodes prefer to connect to already well connected nodes. Early entrants gain cumulative advantage, visibility and funding probability increase with the degree. Part dependence and first mover advantage, early founders benefit disproportionately. Initial conditions strongly influence a long term outcomes. Success breeds success. Okay. uh, uh, Hub formation and centrality dependence. Mentors with many connections became hubs. The network becomes structurally dependent on these hubs. Removing hubs disrupts the ecosystem. Random network ER model that you know, biased versus random linking strategy. Biased linking, inequality and hub dominance. Random linking, slower, more uniform growth. Preferential linking maximizes the visibility faster. This case study assesses understanding of preferential attachment, part dependence, hub centrality, random networks, models, and the impact of bias versus random linking strategy in evolving networks. Okay. So question number 16, what growth process is reflected when early founders get disproportionate visibility? Linear attachment or Gaussian dynamics, preferential attachment, or option D, balanced recruitment? So option C is the correct answer, that is the preferential attachment. Okay. So early founder gains more connection simply because they joined first. This is a classic preferential attachment, richgetricher mechanism. Okay. So option C is the correct answer. Let's move on to the next question, that is question number 17. The firm notices that over time some mentors become too big to fail. Their removal disrupts the network. What property is this? Degree centrality, degree clustering, centrality dependence, richer fatigue, or option D, topological convergence. So here the correct answer is centrality dependence. Okay, because we are more dependent on the hubs. Okay. Certain mentors act as hub, connecting many founders. The network depends on them for connectivity. This is an example of centrality dependence. So option B is the correct answer over here. Okay. Move to question number 18. If the startup network were formed using the ER model, what would the degree distribution resemble? Power law, uniform law, binomial, exponential. So startup network were formed using the ER model. If we are talking about the ER model, then we know that the curve that we get, that is the binomial distribution. Okay, ER model, each link is independent and equally likely. The degree distribution follows a binomial approaching Poisson for large networks. So option C is the correct answer. Okay, so this is a property of ER model that we have already discussed. Question number 19. Founders are encouraged to connect with mentors having more connection. What does this form of guided linking indicate? Negative assortivity, uniform exploration, directed random walk, or option D, biased linking strategy. Okay, so this is known as biased linking strategy because we are biased towards connecting to the mentors having more number of connections. So that is why option D is the correct answer. Choosing nodes based on the degree popularity rather than at random is bias linking strategy. So option D is the correct answer over here. Okay. So let's move on question number 20. A new startup decides to link to random mentors rather than popular ones. Over time, how this will affect their visibility compared to those using preferential linking? It will rise faster? No. It will decline faster? We don't know. It will remain flat? It will grow more slowly. So option D is the correct answer over here. It will grow more slowly. By ignoring preferential attachment, the startup misses out the richgetricher effect. The visibility will grow but slower than those using the preferential linking. So that is why option D, it will grow more slowly, is the correct answer. Okay, so option D is the correct answer. Okay. So by this we have ended the we have ended the case number 4. This is a case regarding preferential attachment only. Okay, so it follows the richgetricher model, but again a more depth towards preferential attachment and linking strategy. Okay. So this is the by this we have ended the case number 4. We are left with two cases, case number 5 and case number 6. Okay, so let's see the case number 5. Case number 5 is the rise of book talk influencer. Okay, so we have this social network known as book talk. So the rise of book talk influencer. Book talk is a social sub network where a few book reviewers consistently get massive views while others stay hidden. The more views a reviewer gets, the more they are promoted by the algorithm, creating massive disparities in visibility. Okay. So theory is required here. The rise of book talk influencer here. Social platform can be a model as network, visibility, view, and recommendation act as edge that reinforce the popularity. Algorithm can reshape network growth dominance. Okay, notes. Creators with more connections, view followers, gain one faster. Algorithm make promotion intensify the richgetricher effect. Popularity is self-reinforcing. Recommendation system, algorithm bias and feedback loop. Recommendation system can create positive feedback loop, increase exposure, more engagement, and more exposure. Okay, this leads to extreme inequality in visibility. Weakening preferential attachment, actively promoting low degree or new nodes reduces the inequality. This intervention, weak preferential attachment dynamics platform can intentionally alter the network evolution. Okay. Scale free network and power law structure. Preferential attachment produces power law degree distribution. A few nodes dominate visibility, most remain obscure. Then we have this small world property and average path length. Despite sparsity, scale free network often have short average path lengths. Okay. Average path lengths grow logarithmically with network size. Hubs dramatically shorten the paths between the nodes. So this case study assesses understanding of preferential attachment, algorithmic amplification, scale-free network structure, power law behavior, and small world property in the social network. Okay, so which concept does this highlight? Uniform information diffusion, preferential attachment, homogeneous propagation, or network symmetry. Okay, so it is question number 21. It is preferential attachment again. Okay, popular reviewers get more views because they are already popular, and algorithm promotes them further. So this is the classic rich get rich mechanism. Example, preferential attachment. Option B is the correct answer. Question number 22. If the book talks recommendation engine were redesigned to prioritize new creators with fewer followers, which dynamic would be weakened? Preferential attachment, network clustering, information entropy, or assortivity. So option A is the correct answer. That is, preferential attachment will get weaker. Prioritizing new creator reduces the advantage of already popular creators. Okay, which is preferential attachment effect. Okay, so option A is the correct answer for question number 22. Okay, let's move on to the next question. In a power law network, which property is true about the average path length? It is always high due to sparseness. It grows logarithmically with network size. It grows linearly with nodes. It remains constant. So again I am repeating, in a power law network, which property is true about average path length? It is always high due to sparseness. It grows logarithmically with network size. It grows linearly with nodes, and option D, it remains constant. So actually option B is the correct answer. It grows logarithmically with network size. Despite hubs being highly connected, most nodes are low degree. Small world property, average path length grows logarithmically with network size, not linearly. Okay, so it grows logarithmically with network size is the correct answer. Option B is the correct answer for your question number 23. Okay. Okay, so by this question number 23 we have ended our case number 5. So we are left with the next case, that is the last case, case number 6, breaking the backbone, that is network attack again. Third case was also network attack, where we have seen a cyber attack on the city. Okay, now here again we have a network attack. Security researcher simulates attack on a communication network. They target either a random low degree router or high traffic core router. Strategy B, cause total collapse of the several sub networks. Okay. So what theory we require? Network topology and degree distribution. Real world communication system can be modeled as graph. Nodes differ in how many connection they have. Topology strongly affects the robustness. Scale free network, we have seen hub nodes and structural backbone. We have seen preferential attachment, random failure versus targeted attacks, and 6 is the power law behavior in real system. 7, network fragmentation and loss of giant component. Everything we have studied, so I am not repeating again. Okay. This case assesses understanding of scale-free network, topology, preferential attachment, hub-based connectivity, and the vulnerability of networks to targeted attacks. So let's start with the question to gain more insights. What does this suggest about the underlying network topology? Homogeneous degree distribution, scale-free with critical hubs, tree-like with no redundancy, or option D, clustering. So option B is the correct answer because power law will be uh, will be followed, and it is a scale free with critical hubs. Okay. So random attacks on low degree nodes have little effect, but removing high traffic core routers collapses the sub networks. Okay. This is a hallmark of the small scale free network where critical hubs hold the network together. Okay. So option B is the correct answer for your question number 24. Move to question number 25. In a BA model, which node's characteristic define how likely it is to get new connection? Age of node, distance to root, existing degree, or option D, node level. So it is very easy. Option C is the correct answer, that is the existing degree. So BA model, new nodes attach preferentially to existing nodes with high degree. So option C is the correct answer over here. Move to the question number 26. Which of this real world system would most likely exhibit a power law behavior? Daily temperature reading, road traffic between the cities, number of followers on social media, option D, employee salary in a government office. So very easy, that is number of followers on a social media. Option C is the correct answer. Power law distribution occur in a system with richgetricher dynamics. Social media followers naturally follow a power law. Few have many followers, most have few. So option C is the correct answer, that is number of followers on the social media. Okay. So this ends our question number 26. Let's move on to the next question, that is question number 27. Which statement is true about scale-free network? Most nodes have a similar degree. Degree distribution is Gaussian. Hubs emerge naturally. They resist targeted attack. True about true about the scale-free network. Most nodes have similar degree. False. Degree distribution Gaussian, false. Hubs emerge naturally. This is true. Okay. They resist targeted attack. They could not resist targeted attack, but they can somewhat resist the random attack. Okay. So option C is here the correct answer. In a scale-free network, however, just naturally due to preferential attachment, most nodes have low degree and the degree distribution is not Gaussian. So hubs emerge naturally. Option C is the correct answer. Let's move on to the last question, or last question of this case, or last question of our discussion. If a scale-free network is repeatedly subjected to targeted removal of hubs, what typically happens? The network grow more efficiently, small world properties strengthen, network breaks into smaller disconnected component. Option D, the network self heals instantly. So option C is the correct answer, because as we are doing targeted attack, we are removing the hubs. Okay, removing the hub fragment the network into smaller disconnected component, because the hubs maintain overall connectivity. Okay, so option C is the correct answer, that is the network breaks into smaller disconnected components. Okay, so with this we have discussed all our question answer part. We have discussed 6 cases. Okay, 2 cases, 4 cases, I can say 4 cases with this preferential attachment and richgetricher phenomena, and 2 cases were attacks. Okay, attacks on node survivability, network survivability. Okay, so by this we have ended the question answer session. So before closing this session, let me just show you some of the codes which will be interesting to you. Okay, so just let me show this codes. Okay, codes that will be helpful for this week. So this week we will be talking about this tree. Okay, so we will be talking about central limit, we will be talking about Barabasi and BA model and ER model and attack survivability. Okay, so let's open it one by one. So let's open it first, that is the central limit model. So central limit model, it demonstrates how independent random factors combine to form a normal Gaussian distribution. Okay, as the distribution of the sum or mean of n independent and identical distributed variable approaches. Okay, so let me just show you the curves. Okay, that will better help you understand. So this is the value of sum. Okay, and x-axis we have value of sum, y-axis we have probability density. Okay, so this is the normal fit. Okay, sum of one independent factor. When we have done sum of one independent factor, then this is our curve. Okay, when we have let me just cancel it. Okay, so then what we have done, this is the sum of one independent factor. Now we have randomly added another independent factor, and this is the curve of sum of two independent factor. Now we have more bell shaped curve. Okay, then we have sum of 5 independent factor, we have sum of 50 independent factor. So observe how the flat distribution become a bell curve as we are increasing the more number of independent factors. So this theorem is known as central limit theorem. Okay, so this is a very important theorem. So this is an important code, so I just wish everyone will see this code and how the result spans. Okay, so this is regarding the central limit theorem. Now we move on to the BA model, or the BA richgetricher model here. So BA richgetricher model, so initially all the networks have similar degree, but then after adding more number of nodes, first we have this only 3 nodes, but adding more number of nodes, what will happen is we are getting richgetricher phenomena. Large hub is emerging. Okay, you can see large hubs. Okay, so like 1 2 3 4 5 6 6 7 large hubs you can see. So this is the BA model or the richgetricher model. Okay, so you can just see the code. So I have given the code according to all the steps. Just follow the steps, just see the code, and again it is a very important code. Okay, so top 5 degree in the network is 20, then 18, 16, 15 and 15. Okay, these are the top 5 degree of the connected network. Okay, initially we have the three node network, and then we have added the nodes one by one, and the nodes prefer already higher degree nodes. Okay, and at last this hubs emerge, and we have hubs with highest degree 20, 18, 16, 15 and 15. Okay, so these are the top 5 degrees in the final network. Okay, so this is the BA model. Now we have the random graph ER model on attack survivability. Okay, so ER model, you can see here giant size. Initially we have this giant size, then we have this random failure with 80, and then we have force attack with 74. Okay, so this is the effect of the attack survivability on the ER network. Okay, so this is the thing. So as we are doing this on the ER model, you can see the giant component, still the random failure is less. Okay, so initially we have 100 nodes, now after random failure you have 80 nodes, and after force attack you have 74 nodes. Okay, so this is the ER graph and the attack survivability. Okay, so these are the these are the 3 codes that I have given you: central limit theorem, and then BA code, and then ER with attack survivability. Okay, so with this I am ending the session for today. Okay, so as no one was in the meeting, only 2 participants were there, and that also with time. Okay, so you can all enjoy this video on the YouTube channel. Okay, and we will meet on the next Tuesday same time, 6 to 8 p.m. Okay, bye.